Imagine you've got this massive billion-word manuscript, right? And just a single tiny typo in all of those pages somehow manages to completely ruin the entire story. Well, that is essentially what happens in cystic fibrosis. So let's dive right into this explainer where we're going to track the microscopic origins of this devastating disease all the way to the futuristic nanotechnology that is currently racing to cure it. We're going to explore exactly how one missing microscopic piece translates into a massive, widespread systemic disorder across the body, and more importantly, how modern science is gearing up to rewrite that underlying code for good.
I absolutely love starting here because to truly understand the devastating impact of this disease, we first have to zoom all the way in to a single missing genetic letter. Cystic fibrosis is an inherited monogenic disorder. And what that means is, it doesn't take some complex, mysterious web of interacting genes to cause it. It originates from just one specific broken link in our DNA that gets passed down from our parents. But, as we're going to see, that single missing piece triggers this massive cascading failure across multiple vital systems, severely impacting mucosal surfaces throughout the entire human body.
Here's our roadmap for today's explainer. We'll kick things off with the microscopic genetic typos and the resulting mucus chain reaction. Then, we'll look at the current treatment gap before exploring how we are rewriting the genetic blueprint and physically breaching the mucus barrier. Let's get to it.
All right, Section 1, the microscopic typos. We begin our investigation at the root cause, located squarely on chromosome 7.
So the crucial point here is that CF is caused by autosomal recessive mutations in this specific blueprint. To break that down, autosomal recessive basically just means you have to inherit a mutated copy of this gene from both of your parents for the disease to actually manifest. Now, this specific gene encodes the CFTR protein. You can think of this protein like a microscopic water pump. It's this specialized cellular gatekeeper whose sole job is to gate the flow of chloride and thiocyanate ions across the membranes of your epithelial cells. When this pump is working perfectly, it perfectly regulates your surface hydration. But a mutation here completely breaks this cellular machinery, and it stops the vital movement of salt and water dead in its tracks. Now, in the vast, overwhelming complexity of the human genome, you might expect dozens of different, widely varying mutations to be responsible for a disease like this. But get this number is absolutely staggering. Roughly 80% of all CF cases globally stem from one specific classic processing mutation known as F508del. We aren't talking about a scattered landscape of genetic errors here. This single variant holds the vast majority of the clinical weight around the entire world.
Let's trace how this builds a cellular factory, typo. Think of the cell's endoplasmic reticulum like a super overzealous factory inspector. First, a tiny 3-nucleotide deletion removes a single phenylalanine residue at position 508. Because of this one tiny missing piece, the resulting protein severely misfolds. Now, that overzealous factory inspector, the cell's quality control machinery, recognizes the defect, flags it, and sends it straight to the cell's garbage disposal. This disposal system, known biologically as the ubiquitin proteasome pathway, completely destroys the gatekeeper protein before it can ever even reach the cell membrane to do its job.
Section 2, the mucus chain reaction. Now that we know the channel is completely missing, we can explore the biological fallout that happens on the surface of our cells.
This brilliantly illustrates the whole domino effect. Without that chloride transport, the normal movement of salt and water across the tissue entirely collapses. The tissue suffers from this massive hyperabsorption of sodium, which relentlessly dehydrates the liquid layer. It literally turns what should be a slippery, highly protective mucosal shield into a thick, sticky layer of glue. This highly viscous matrix anchors itself to the microscopic hair-like cilia in your airways, and it creates an absolutely ideal, undisturbed environment for chronic bacterial colonization. And because epithelial tissues line so many of our vital systems, this single genetic error creates a massive, widespread crisis. Let's break this down system by system, right? In the respiratory tract, that thickened mucus plugs up the small airways, leading to opportunistic bugs like Pseudomonas aeruginosa setting up shop. Over time, this chronic infection causes permanent airway widening, which is a very serious condition known as bronchiectasis. Moving to the gastrointestinal system, those viscous secretions physically block the narrow ducts of the pancreas. Because of this, essential enzymes simply can't reach the gut to break down food. This leads to severe fat malabsorption, a condition known as steatorrhea, which causes greasy stools, severe nutritional deficiencies, and eventually even CF-related diabetes. And in the sweat glands, this broken machinery prevents the reabsorption of salt, leaving individuals with abnormally high chloride concentrations in their sweat, putting them at a much higher risk for extreme salt loss and hyponatremic dehydration.
Okay, moving to Section 3, the treatment gap. We have incredible temporary fixes today, for sure, but we really need to talk about why they aren't enough to end the disease completely.
Right now, our frontline defense involves small molecule CFTR modulators, specifically a combo of breakthrough drugs like elexacaftor, tezacaftor, and ivacaftor. These act as incredibly effective structural chaperones. They basically hold the hand of those misfolded F508 del proteins we talked about earlier, and they physically help guide them to the membrane so they can finally function. Over the last decade, these treatments have been nothing short of miraculous. They've fundamentally changed the life expectancy and daily reality for thousands of patients. But, and this is a big but, while they are life-changing, they do not fix the underlying genetic blueprint. They require constant daily dosing. They are treatments, not permanent cures.
And here is the critical gap in all of this incredible progress. Roughly 10 to 20% of patients have what we call null or nonsense mutations. These individuals synthesize absolutely zero CFTR protein. Their cells simply do not produce the gatekeeper at all. This means those miracle structural chaperone drugs we just talked about, they offer them absolutely no clinical benefit whatsoever. I mean, you simply cannot hold the hand of a protein that literally doesn't exist. So for a definitive, permanent cure that helps everyone, we have to go deeper.
Section 4. Rewriting the genetic blueprint. To help everyone, including those null mutation patients, scientists are actively racing to fix the actual source code itself.
So early gene editing was honestly a bit like using a sledgehammer to fix a watch. The initial CRISPR-Cas9 strategies relied on creating double-stranded DNA breaks. Unfortunately, this triggered totally unpredictable insertions, deletions, and heavy cellular toxicity. This is especially dangerous in non-dividing airway cells, which are incredibly delicate and just cannot easily recover from a sledgehammer blow to their DNA. But modern base and prime editing? Entirely different ballgame. It acts exactly like a highly precise search and replace text processor on your computer. By changing single nucleotides, scientists can introduce targeted revertant mutations. This effectively rescues the CFTR function by bypassing the original genetic defect entirely, and they can do it without making those dangerous, destructive double-stranded cuts.
But, just editing any random cell on the surface isn't really enough. The differentiated cells lining our airways are constantly shed and replaced, much like our skin cells. For a genetic correction to last a lifetime without requiring continuous repeated redosing, the editing machinery must reach the deep airway basal stem cells nestled way down within the airway walls. If we can successfully correct these specific parent-progenitor cells, we've effectively cured the disease for the lifetime of that tissue. Every single future generation of daughter epithelial cells will be born healthy, naturally carrying the functional CFTR gene, moving us entirely away from daily treatments to a potential one-time fix.
Section 5. Breaching the mucus barrier. Because having the perfect genetic editor means absolutely nothing if we can't physically deliver it through that thick, dehydrated mucus wall we talked about earlier.
This step-by-step delivery system is just an engineering marvel. The most stubborn barrier to a functional cure is the physical delivery of the editor. So to bypass this, researchers are utilizing non-viral vectors, specifically selective organ targeting or SORT lipid nanoparticles, paired with biodegradable polymers. Think of these nanoparticles as microscopic Trojan horses or stealth ships. Their sole job is to securely wrap up and shield the incredibly delicate genetic payload from the body's immune system, which would normally destroy it on site. These stealth ships are optimized to be delivered directly into the lungs through a simple, inhalable mist, allowing for non-invasive uptake straight into the deep airway epithelium.
And scientists at the highly anticipated upcoming NACFIC 2025 are essentially working on a massive, complex, microscopic packing problem to make this reality. The future of these nucleic acid-based therapies hinges on a crucial dual approach. On one hand, researchers are actively focusing on shortening the gene sequences themselves, optimizing the payloads so they can fit perfectly inside these targeted delivery vectors. Simultaneously, they are aggressively enhancing and engineering those SORT lipid nanoparticles to be tough enough to physically punch right through that stubborn, thick, protective mucus barrier.
It's really incredible to think about this whole journey, right? From a single missing genetic letter on chromosome 7 all the way to the massive systemic hurdles of cystic fibrosis. But knowing that we can now physically rewrite the biological source code using precise base and prime editing, and that we're actively developing advanced stealth nanotechnology to bypass the body's toughest microscopic defenses, well, it forces us to look forward. The question isn't if we will cure cystic fibrosis. Rather, are we standing on the precipice of a future where genetic diseases like CF are permanently edited out of human existence? And if so, how soon until that future is our reality?